Bimolecular nucleophilic substitution involves backside attack and inversion of configuration. So we often need to think carefully about stereochemistry when the SN2 mechanism is operating to ensure that we depict inversion of configuration. In SN1 reactions, thanks to the carbocation intermediate, as we'll see, stereochemistry is somewhat less important, and there's a complete lack of stereoselectivity in many SN1 reactions. And so we typically end up with a racemic mixture of enantiomers when a chiral product forms from an achiral starting alkyl halide. And even when a chiral starting alkyl halide is used, we often end up with a racemic mixture of two enantiomers. The reason for this, the basic reason, is that the carbocation intermediate of SN1 is trigonal planar and flat. And this makes it generally achiral, assuming there's not another stereocenter somewhere in the molecule. The carbocation has a plane of symmetry that is the trigonal plane, and you can see an example of that here. This carbocation is planar, and it's got this plane of symmetry that's more or less perpendicular to the screen. Because the carbocation is planar and flat, the nucleophile can approach either side, and we expect a mixture of inversion and retention of configuration, and naively, barring some memory effects of the leaving group, which we'll touch on here in a second, we would expect a racemic mixture of products. And let's see how this works by pushing some curved arrows. And so we're starting here actually with a chiral alkyl bromide, and the goal is to determine whether the reaction is stereoselective or not, right, in the case of SN1. In an SN1 reaction of this substrate, the bromide will depart, and we get this planar carbocation intermediate. We've actually gone from a chiral starting material to an achiral reactive intermediate right here. The nucleophile then comes in. And the nucleophile, because this molecule is planar, the carbocation is planar, can approach from one side or the other. It can approach from kind of the left-hand side, forming a bond on that side of the cation. This leads to the product here and is associated with inversion of configuration. Notice the nucleophile is on the opposite side from where the bromine was in the initial substrate. Or it can approach, the nucleophile can approach the right-hand side of the cation, in which case we get this product, and this looks like retention of configuration with the nucleophile on the same side as where the bromine was in the initial alkyl halide. And because the carbocation is completely flat, the energetics of both of these approaches are identical, and we would expect a 50-50 mixture of inversion and retention, or a racemic mixture of the two enantiomeric products. These are enantiomers. Notice each one is now back to being chiral because we've pyramidalized the central carbon again, and they're enantiomers. They are related as mirror images. So in general, when SN1 forms a chiral product from an achiral carbocation, we expect a 50-50 mixture of the two enantiomers, or a racemic mixture. Now, in some cases in SN1 reactions, we actually see a slight preference for inversion of configuration, which is kind of interesting. It suggests sort of a continuum of mechanisms between SN2, which is fully concerted, and SN1, which is fully stepwise. The idea of a preference for inversion of configuration in SN1 is that the leaving group, is not completely gone when the nucleophile starts forming its bond. In that case, we have what we might call an intimate ion pair between the carbocation and the leaving group anion. So bromide is not completely dissociated from the carbocation, we might imagine, right? There's some, for example, ionic attraction between the negative bromine and the positively charged carbon. And that association means the bromine is taking up space on the right-hand side of this carbocation. This inhibits nucleophilic attack to some degree and leads to a preference for inversion of configuration and enrichment in this enantiomer in the product mixture. So we actually see a little bit more of this enantiomer than the one derived from retention of configuration, which would require the nucleophile to kind of shove its way through the bromine, through the bromide anion, which is not as hard as I'm making it sound, and so this preference is often not great, but it is something we can observe in the case when an intimate ion pair forms. And intimate ion pairs are actually more common in solvents that are less good at stabilizing ions, right? As the dielectric constant goes down, these ions tend to want to get closer to each other since the solvent is not satisfying their need for intermolecular forces, we might say. And so there's a solvent dependence to the enantiomeric composition of the product mixture that's actually fascinating to think about.